Yeah, so welcome back. In this video series, we are going to talk about binary search trees. Before that, let me give you some brief idea about trees and then binary trees, and then we'll move to the binary search trees. So let's take a very familiar example of hostel setup where what we have is on top we have chief warden, and below it we have your boys hostel warden. Then we have on this right hand side we have girls hostel warden. Then we have a male caretaker for this boys hostel, a male security staff for this boys hostel. On this side we have female caretaker and the female security staff. So what we see is that we see a top down hierarchy, and where we see chief warden to be on top, and subsequently we see various people associated with the hostel and at lower levels in the hierarchy. And this particular hierarchical structure is represented using a tree, where what we have is we have several options, like we have this particular node and we give a special term that we'll see in the next slide, and then we have these nodes for which we have special terms for these set of nodes, the intermediary nodes. So let's see one by one what all these things are. So to start with, what we have is we have like chief warden on the top, and this is the single node, and which is called as your root node. And what is happening is that the root node set has only one value. That means it will only have a single value, which is your chief warden, this particular set, right? And then below it we have this second levels, and the last one is your leaf nodes, and this particular set will have all these four values. So in this particular set what we have is these four values we have in this particular node, and we give a separate dedicated term to this particular thing as well. And in between, right, so this is the topmost layer, this is the bottommost layer, and in between whatever we have, it's like the intermediary ones, right? So these two are nothing but the intermediary ones, so these two. So let's talk about leaf node, and what we see is that the bottommost layer in the hierarchy will be having the leaf nodes, right? So this one, this one, this one, and this one. So all these four are your leaf nodes in a tree. And this particular leaf node has a special characteristic. First of all, of course, it is the bottommost layer, and then what we see is that we don't have, right, all these childs added to it. So what we say is that leaf nodes have no children. That means there will be no left child or right child for all these four elements. But yet when we compare, that means there are two things. One is your root node, another one is your leaf node. So what you see is that this will be having a singleton set, right? So for this I'll always get a singleton set. For this we'll have we can have singleton as well as multiple value set, and you may come across a situation where I only have this particular node in an entire tree. That kind of situation also we may come across, right? So what we see is that we only have chief warden in this, and we don't have rest other nodes in it. So that's one of the way to identify the leaf nodes, right, which is that the nodes which are not having any left or right child, right. And the case which we were talking about, where we said that okay, there is a possibility that I only have this particular set. In that case, it's like I only have this kind of tree where a single node exists, which is the root node, right? No left or right child. So that kind of setup we have in this. Now next is the levels of the tree, right? We saw a hierarchy, right? So definitely when in a hierarchical structure, what we see is that there will be a top-down hierarchy or maybe a bottom-up hierarchy, but yet there will be some amount of hierarchy which will exist. So that is displayed with the help of these levels, right? And in some of the literatures you will find the depth, some of the literatures you will find the height of a tree, but almost all the things are same. It depends on how we consider a particular problem, right? So what we do is that for any particular tree, your root node, right, so this particular thing will be at a 0th level, and subsequently will keep on increasing. So this is at 1th level, and this is at a 2nd level. So that's how your hierarchy goes on from top to bottom, right? And similarly you can say that there is something called as depth. So slightly in some of the literatures you will find slight variation in the definition. So in that case, I'll take a small example to give you the detail about what basically the depth is. So let's take one example. So what we have is we have this kind of tree, right? Now on one side we say that this ends here, whereas on the other side what I see is that this particular thing ends here. So that's why this particular thing will be added, and that would be your depth. That's the only difference. So don't get confused, right? Even if you are using 0 for this level, 1 for this, 2 for this, then also it's okay. But for effective usage and effective programming, this kind of setup makes sense, right? So it's like maintaining multiple options at 0th level, whereas you may come across an empty tree. What basically the empty tree is, we'll see in the coming slides. So in that case we get an idea that okay, at 0th level nothing is there, so I get an empty tree, right? So that kind of setup we have. Now next thing is your subtrees, right? We were talking about trees. Now we are going to talk about your subtrees. So if I have a tree and it's not an empty tree, that is non-empty tree with some childs, so the left portion and the right portion will be called as the left and right subtrees. And for this subtree you'll say that okay, this is the left and right subtree. For this is the left and right subtree. If suppose I don't have this particular thing, the tree ends here, in that case what I'll see is that this particular thing is my left subtree, this particular thing is my right subtree, right? So it's a kind of subset. So the elements in a subtree will be the subset of the elements of a tree. That's how we denote if we talk about this trees in terms of your discrete mathematics, to be very specific. Now let's now talk about your binary trees, right? So this time we are giving a name to a particular tree, and we are saying that okay, a particular tree will be called as a binary tree when we have either 0 nodes, that means an empty tree, or 1 or maximum 2 children, right? So that means I can have something like this, or maybe an empty tree as well, or something like this, or something like this. But if suppose I find a figure like this, so this particular thing cannot be termed as a binary tree. Now let's go into some more technical details of it. So when we have nodes with 0 children, that would be called as your leaf node, or maybe the terminal node of that particular tree, right? So for this we have this, for this we have this, for this we have this, and this we are saying that this particular thing is not a binary tree or BT. In our discussion for binary tree, we'll be using BT, or in some other literatures you'll find B tree, so that this is also okay. In this particular thing, each node will have a data element, right? Left pointer and a right pointer. So what all options we have? I have a data value, and I have a left pointer, I have a right pointer, right? So due to shortage of space, I've explained in this format, but let me explain the same in the next slide. Right, so what we have is we have a node like this, we have a data value, right? And on this side I have a left pointer, on this side I have a right pointer. Now the root element of a binary tree is pointed by a root pointer. Now so this points towards this, so that means this will be having the address of this particular node. Now if this root equals null, in that case I don't have this particular tree, right? So this indicates that this particular tree is an empty tree, right? So this corresponds to this. Now how we implement it? Once again the same thing. That means I have see in some of the literatures you will find that this particular thing is called as info node. In some of the literatures you will find at this thing as DV, which is nothing but your data value, and in some of the literatures you will find this as DN, which is nothing but your data node, right? In fact, when we say node, so we are talking about the entire node, so data value makes more sense, which we'll also be using in our discussions. And on the other hand, what we have is, on this side we have like your left pointer, on this side I have my right pointer, which is pointing towards my left or right child. And if suppose I have a situation where I have only one tree, in that case, I have only one node, that means my tree is something like this. So the representation of this becomes your data value, this is null, this is null, and my root is pointing towards this part. So let's talk about several categories of this binary tree, and these categories are termed as your efficient binary trees. That means the efficiency in computer science means we are talking about how quickly I can search, how quickly I can delete, how quickly I can insert. So we have several options, which are several variants of binary trees, which are like binary search tree, which is also called as your BST, and then we have RB red black tree, which is also called as your RB tree, which I guess you might be covering in your data analysis and algorithm design and analysis of algorithm course. And then we have your AVL tree. We'll be talking about this particular thing in next few videos. And then we have your TBT, which is your threaded binary trees. This eventually is not there in your course. Then you have your ST, which is your splay trees. So in these set of videos, we'll talk about binary search trees and your AVL tree in the coming slides, or maybe in the coming videos. Now let's talk about binary search trees. So in this particular thing, what we have is that this particular binary search tree, this is termed as BST, is nothing but a variant of a binary tree and is also known as the ordered binary tree, right? So that means the element which are inserted are in some order. That's why it is called as your ordered binary trees. So these nodes are arranged in some order, and the best part is that each node contains some distinct values plus these key values in the tree will be compared by your greater than or less than sign, right? Of course equals to is also added because if suppose I have to compare some values, less than or greater than is always when I am moving towards left or right. What this movement is, we'll see in the next set of videos when we'll talk about various operations on binary trees. Here the key value of each node in the tree is less than every key value in its in its right subtree, and greater than every key value in its left subtree. So what these things are, we'll be able to understand in the next set of slides. So what this particular idea is that, let's say this is the root node. So let's say this is 5. Now if suppose I'm entering another value which is 7, so of course it is greater than this, so it will go on the right side of this particular value, and then we have Z. So once again on this, so it's like right side going, it's going towards right side, right? So this is one of the issues of binary tree. Suppose we are giving values which are increasing, and that too in a sequential order. In that case, what we do is that it will be like left justified or right justified binary search trees, right? So now let's see the basic difference between binary search tree and your binary tree, right? So the basic one is like in the very first one, what we have is that in case of binary search tree, everything is well ordered, right? Whereas in this, the values are unordered, and that's why it is binary search tree is also called as ordered binary tree. On top of it, just because of the virtue of the unorderedness in this binary tree, this becomes slow in case of search or insert or delete, right? Whereas since it is ordered, so the search becomes faster, the insert becomes faster, and the delete option also becomes comparatively faster, right? Just because of the virtue of its ordered characteristic. And what we have is, in case of binary tree, I can have like this thing with a non-linear structure, and that too, it's like if I'm having 5 on this side, I can have 6 on this side, I can have 7 on this side. In this, it's like 5 is on this side. If it is 6, it will be on this. 7, it will be on this, right? If suppose 3, it goes on this side, right? Here I can have 3 like this as well. So these are some of these major differences between binary tree and your binary search trees. And let's take a point and which I think you should ponder, right, on this particular point as well. And the point is that binary search tree is of course an ordered binary tree such that the right and your left subtree are also a binary search tree. That means if suppose I have some tree, right, let's say this is T, this is left subtree, this is right subtree. So by this definition, it says just because of the virtue of the properties of a binary search tree, this T1 and T2 are also your BSTs only, right? So T1 and T2 are nothing but the left subtree and your right subtree. So both the subtrees are also the binary search trees. So we'll talk more about binary